Scaling modern AI requires adding more dense parameters and running global attention across every layer. This forces hardware to process an ever-increasing amount of data, pushing the limits of the largest available compute clusters. The constraint is mathematical. Standard multi-head attention operates on an O of L squared complexity curve. When the context reaches 1 million tokens, the processing time and memory required to calculate every token's relationship grows exponentially, making the system impossible to serve efficiently. Qwen3.8-Flash-Next is the experimental precursor to Qwen4, designed to break the direct link between a model's total parameter count and the compute required to run it. Instead of a 397 billion parameter monolith, this system uses a highly specialized 180 billion parameter structure. The design includes a 125 billion parameter dense backbone, 51 billion parameters of off-accelerator memory, and a 4 billion parameter speculative prediction head. This deconstruction suggests that frontier performance is no longer dependent on maximizing dense parameter counts, but on architectural heterogeneity. During inference, this architecture activates only 6 billion parameters per token. Despite this active footprint, the model performs at a higher level than the previous 397 billion parameter flagship on 8 out of 14 pre-training benchmarks, specifically in STEM and high-order reasoning. It reached this performance problem losing 1/3 of the training tokens and roughly 1/9 of the total training flops compared to the previous flagship. To understand how these reductions were achieved, we will deconstruct the engine layer by layer to see the 4 co-designed mechanisms that enable this efficiency. This 6 billion active parameter engine provides a technical blueprint for serving frontier-level intelligence on accessible local hardware. The 48 layers of Qwen3.8-Flash-Flash are organized into 12 distinct macro blocks, each containing 4 layers. The first 3 layers in every macro block are dedicated to a token mixer called Gated DeltaNet. Gated DeltaNet operates as a linear recurrent associative memory. It replaces quadratic connections with a delta rule update, meaning the model tracks associations over time without the memory growth associated with standard attention. The 4th layer of every macro block uses Qwen Sparse Attention, providing the network with precise capacity over long contexts. In this layer, the sequence is divided into microblocks of 4 tokens each. A compressed indexer scans the sequence, selecting exactly 512 microblocks to process. This limits the core attention calculation to a fixed budget of 2,048 tokens, regardless of total sequence length. This 3-to-1 hybrid ratio reduces prefill latency on long contexts by 65%. It achieves this speed without losing accuracy, scoring 96.8 on the ruler benchmark. By combining fast linear recurrence with targeted sparse attention, the model handles long sequences without the exponential increase in compute. In standard deep networks, the signal from earlier layers can grow weaker as it passes through the stack. In a 48-layer model, this variance in the residual stream often attenuates the contribution of deep sublayers. Qwen resolves this using a gated residual highway, which expands the residual stream from a single path into 4 parallel branches. Element-wise read gates and scalar write gates regulate the flow of data. These gates use low-rank bottleneck projections to determine which information enters each branch and how it updates the total state. These parallel lanes allow the network to specialize. One branch can preserve low-level syntactic information, while another focuses on high-level logical reasoning, preventing the different types of data from interfering with one another. The gated residual highway provides the structural stability needed for deep networks to maintain complex mathematical signals all the way to the output. Mixture of experts models are often limited by GPU memory bandwidth. Adding more active parameters to the accelerator's memory can slow down the generation of every token. Qwen addresses this by moving 51.2 billion parameters, representing 20 million frequent engrams, into the host CPU's DRAM. While the GPU processes the initial embedding and layer 1, it signals the CPU to prefetch specific engrams. The host memory controller transfers these vectors across the PCIe bridge in real time. These parameters are injected at layer 2. Because the transfer time is less than 1 millisecond, it is completely hidden behind the GPU's internal compute time. This design turns standard host RAM into a massive retrieval bank, allowing the model to scale its knowledge parameters without hitting the GPU memory wall. Every layer in the backbone contains 512 fine-grained experts. However, only 11 experts are active for any single token, 10 that are dynamically routed and 1 that is shared. Training a sparse model at this scale is difficult. Standard optimizers like AtomW often struggle with gradient spikes in deep MOE layers, which can cause the training process to fail. The team used a targeted optimization strategy, applying the muon matrix-based optimizer exclusively to the 2D linear weight matrices in the architecture. Muon uses Newton-Scholz iterations to orthogonalize the weight matrices. This process ensures that update magnitudes remain invariant of the matrix dimensions, resulting in much smoother convergence. This optimization, combined with gated norm damping, allowed the team to eliminate batch size warm-up entirely and increase the learning rate to 1 × 10⁻³ . This specific mapping between the optimizer and the architecture prevents the model from collapsing under the stress of multi-trillion token training. When these interlocking components are unified in a post-trained model, the architectural efficiency results in high-level agentic performance. Qwen3.8-Flash-Next achieves 62.5% on SWE-Bench Pro and 58.7% on Deep SWE 1.1, scores that exceed those of much larger proprietary models. It also reaches 91.7% on the GPQA Diamond benchmark for scientific reasoning and 64.4% on the Claw Eval multimodal agent test. For real-world use, a native multi-token prediction head generates 4 speculative tokens at once. This results in an average acceptance of 4.07 tokens per step, speeding up the generation process by a factor of 3. During long horizon tasks, the model can use a preserved thinking mode. By retaining reasoning traces in its context, it avoids repeating complex logic and increases the efficiency of the KV cache. The performance of Qwen3.8-Flash-Next suggests that frontier AI now depends more on the precise coupling of hardware and software than on the simple addition of more compute.